Hello, I'm Vlad. I'm very glad to present some d orbital splitting in regard to the International Chemistry Olympiad. And here is what you should know for the year 2022, the Olympiad in China. First, most important point is that there are in principle different splittings of d orbital levels. It doesn't matter how we label them. What matters for you is that when you have octahedral coordination or environment, let's say so your ion in a solid occupies an octahedral hole, then its d energy levels will be split into set of 3 and a set of 2, like this. 3 below, 2 above. Remember that. If your ion is in a tetrahedral hole, then you will have a splitting like this. 2 below and 3 above. And that is most important, you should remember. You might be asked to draw the labels, but this is also very, very easy. This is a d orbital, and this is yz, xz, xy. So you have multiplication of the labels for the axis x, y, and z. And then you have square x squared minus y squared, and then you have z squared. You don't at the moment need to memorize it. It is kind of useful, but it is not so crucial. What is crucial is that you remember for octahedral, 2 above, 3 below. For tetrahedral, 3 above, 2 below. The second most important point here is that for some configurations you can have high spin and low spin. And that is basically about pairing your electrons when you are feeling the energy levels. For instance, if you have one electron, then of course it goes to the energy level which is lower in energy. When you have two, you put them, according to the Hunt rule, you put them on different orbitals, which is logical because they repel each other, they don't want to move in the same space. So when you have 3, you put them on 3 different orbitals, but when you have 4, you have now an option. The thing is that due to splitting in this octahedral environment, 2 energy levels will be higher in energy, and you could put electrons there and still stabilized by so-called exchange interaction. However, and that corresponds to the Hunt rule somewhat, but if the difference between those energy levels is big enough, then you can pair your electron, and that would be low spin because you see only 2 electrons are parallel. This is paired, and here on top you have high spin because you have 4 electrons with the same, let's say, direction of the same type. And that's it. So it's so easy for different ions. You have all these configurations which are considered as high spin. Well, this is not a very high spin, of course, but this is something that you cannot do. It belongs to 2 of them. Anyway, the low spin is when you pair electrons together. And that is what you should know. And probably if we go now into the details, then there is some kind of theories where you can quantify the difference between octahedral and tetrahedral splitting, and you can use the parameter which is called the splitting parameter. And overall, it is chosen such that if you fill all these levels and then somehow calculate the energy levels in relation to this body center, you would need to calculate by this difference in energy, which is 3/5 of delta O. This is called delta O. It's not shown here for some reason, but it is. Then, okay, so if you do the summation for the completely filled energy levels, you will just get 0. That's it. But if you have only 6 electrons, then the stabilization will be this 2/5 multiplied by 6. And then there is this also quantitative relation that for tetrahedral, the splitting parameter is 4/9 of octahedral. We actually don't need to know this most probably for this IChO in China, but it was just a year ago in Japan where you had to compare the stabilization energies of different ions in different environments. So you just now be aware that there is a quantitative approach to describe the stabilization energies in different environments, like in octahedral and tetrahedral, and also for different configuration, considering how many electrons you have on each energy level. Right, so here's an example for stabilization energy. For octahedral, we can consider high spin and we go through all possible configurations. Now we consider low spin, we just take all possible configurations and then we calculate in the units of delta O what would be the stabilization. And now you can see for D5 the stabilization energy is 0, but if you have low spin it might be 2. So we could conclude that in some, if this number is actually higher than the pairing energy, then the complex will be low spin. So now it depends on the pairing energy because the stabilization shows how much energy will be gained. No, maybe. Yeah, okay. So how much energy will be gained just by putting them onto the energy level, but we must pay the price for pairing them as well. Good. We can go to the last point, solve the problems. And if you check the link at our Moodle course, then you will find some set of problems from Austria Chemistry Olympiad, where it is very popular to calculate the stabilization energies, and some IChO problems. But